Okay, and I'm gonna share something with you. Is it? There we go. Okay, so can everybody see this graph here? So we've got a graph of here. We notice we have the function x squared. Okay, and you notice here that I've drawn a tangent line. All right, I've drawn the tangent line. And what I've plotted here, this point that you see here, is the value of the derivative at that point. So if you look at x equals 1, look at the slope of the tangent, and it looks like, as you know, x goes up by 2, y goes up by, 1, 2, 3, 4. So it looks like the slope seems to be about 4 over 2 is 2. Okay, and look at that. What's the y value? So this represents the derivative. So what I'm going to do is I'm going to move this point on the graph, meaning I'm going to move the slope of the tangent, and it's going to draw the derivative for me. So essentially, it's going to draw the derivative function. All right, so let's have a look here. Now, given that the function is x squared, what do we expect the derivative to look like? What type of function should it look like? Can somebody tell me what type of function the derivative of x squared should look like? I mean, we should know the answer.
A parabola?
No, the original function is a parabola,
Way.
2x. But if we take the derivative, x squared, if we take the derivative, we get 2x. What would 2x look like?
A straight line.
Exactly, a straight line. So let me do that here. I'm going to, oops, that's not what I want to do. Let's see if I can get this here. Well, I'm not sure why it's doing that. Let's try again. This is an old program. And we see that as I move the point, you see, not surprisingly, the slope gets bigger and bigger and bigger. And then when I move towards 0, hey, the slope gets smaller and smaller and smaller until we get to 0, where we have our horizontal tangent. And then as we move, you see it's getting more and more negative. And if we look at this line, well, again, let's find the slope of this line. As x goes up by 1, y goes up by 2. So and it passes through 0, 0. So this is the function 2x. Okay. And here, okay, let's look at x cubed. Again, what's the derivative of x cubed? It's 3x squared. So the derivative should look like a parabola. Okay. So that's the problem. Let's do this. That, and let's move this around, and we see it's getting steeper, steeper, steeper. But now when we move to the left, it's getting less steep, less steep, less steep, less steep, less steep. Eventually it becomes 0. But when I keep moving to the left, the slope is still positive. And look at that. It just creates a parabola. Okay. So what we see here is that the derivative of this cubic function is a quadratic function. Okay, and let's look at one more here, just for the fun of it. Okay, let's make this a bit bigger here. Okay, so you see I'm starting with a cubic function. Okay, and let's, yeah. Sorry, was there Jalen?
Oh, sorry. I didn't mean to. My mic was accidentally on.
Oh, okay. And now let's move it around. So you see how it's getting less and less steep. Eventually it's approaching 0. There you go. Slope of the tangent is 0, so the derivative is 0. And then we move and it starts becoming negative, more negative, more negative, more negative. And then at a certain point, it starts becoming less and less negative until we eventually get to 0. Okay, and then what happens? It starts to get positive again. But here we're seeing that the derivative of this cubic function is a quadratic function. And who's going to tell me why that's not surprising? Why do we expect the derivative of a cubic to be a quadratic? Can somebody give me a quick reasoning as to why that's very reasonable?
Because of the power rule?
Exactly, because of the power rule. Because anytime we take the derivative and imagine the highest power, if the highest power is a cubic, then when I take the derivative, it's going to become that version, that portion is going to become quadratic. If the highest power is x to the 7, means when I take the derivative, the highest power of the derivative is going to be 6. So it's going to be a 6th-degree polynomial. Okay? So as you take derivatives, the power goes down by 1. Okay? So let me now share my other thing again. All right, so this is where I have to make a decision as to whether I do what I normally do when I teach the product rule and the quotient rule, or do I do something a little different? Because when I teach the product rule and the quotient rule, I always prove them. I don't just kind of give it out. But I was looking at what Brightspace does, and it kind of makes you do this, I don't know, to me, a bit of a silly, it's a bit of a silly exercise on how to find the product rule. I don't think, I wouldn't say it's worth your time doing that. But having said that, I'm not sure if you guys really do proofs in this course. So I'm going to take a little bit of a poll here. I'm sure there's a way to do it on, let's see, is there a way to take a quick poll on Teams? Well, if there is, I don't see it. So I'm not going to try to figure that out now. So are there people who want to see the proof of the product rule, or do they just want to have the formula and then we can work with it? And similarly, I don't know if I'll have time for the quotient rule. That wasn't something I was supposed to do today, but I can do it if we have time. Are there people who want to see the proof of the product rule? It's kind of nice because it's, a bit of a trick. It's not the easiest thing in the world, but it's not too difficult either. But it's going to take about probably 15 minutes to go through it, and then we can apply the product rule. So let me let's just check the chat. If you want to see the proof. So I see one, sure. Anybody else that we have who wants to? I see one, no. Anybody else? It's funny, when I'm teaching on here, I'm not sure how many people are out there. So I'm only seeing 2 votes here, one no and one yes. So I need one more vote. Oh, wait, I see what you're doing. You're creating a, sorry, good. I guess you folks know how to do this. So far we're up to 4-3. Okay, so if you don't want to see it, you better speak up now, because right now the yeses are winning by 1. Well, winning by 2. I'm leaving you 5 seconds. If you don't want to see this, you better speak up now. Oh, 7. Holy moly. Okay. I think the no's are going to be able to catch up. Okay. I'll try to go through this as quickly as possible. Okay. So we want to find the derivative of f at x times g of x. Okay. And if we want to prove what the formula is going to be, well, you have to go back to the definition of the derivative. So you have to go back to the limit definition. So I'm going to put this into the limit definition. Okay. The limit as h approaches 0. So now my function is f at x times g of x. Okay. By the way, the other nice thing about proving it is here, notice I'm not using a specific function f or a specific function g. Meaning if I can prove this, it means it works for every pair of functions. Okay. No matter what. So that's what's nice about proving things. Okay. So let's apply the derivative formula. So I need to evaluate this at x plus h. So I have f at x plus, so wherever I see an x, I replace it with x plus h, and then minus the function evaluated at x, so just f at x, g of x, okay, all over h, okay? And so now we need to find a way to manipulate this so we get some sort of formula. And the problem is I don't see any way I could manipulate this expression at all. There's nothing I can do. I don't know what the functions are. I don't have a common factor between the first term or the second term. So it's actually looking a little hopeless at this point here. Okay. Let's try to think about where we might want to head. All right. So I know that the derivative of f of x times g of x is not the product of the individual derivatives. But does it seem reasonable that whatever formula I come up with should have the derivative of f and the derivative of g as part of it? At least we would hope so. Okay, doesn't that make sense? That if I want to try to find a formula for the derivative of this product, the derivatives of the individual functions should somehow be a part of it. Okay. And this is where, and this is the thing about some proofs. Some proofs, it's very obvious on what the steps are going to be. And sometimes there's a proof where some very smart person had to have a really good idea at some point. Okay. So on the side, I'm going to remind us what the derivative of f at x would look like. It would be, f at x plus h minus f at x over h, and then the derivative of g would look like this. The limit as h approaches 0 of g of x plus h minus g of x over h. Okay? So what we need to try to do is we need to try to manipulate this expression so somehow I can get these expressions to show up there. And let's take a look here. The f at x plus h minus f at x. Can you sort of see that if this had a g of x plus h, what could we do? Let's say instead of this was g of x, it was g of x plus h. What could we do in this numerator if I had the same factor on both terms? Let's just say we had f at x plus h times g of x plus h, minus f at x times g of x plus h. What could we do with this g of x plus h?
Factor it out.
Yeah, you could factor it out. And what would you be left with inside your bracket? F at x plus h minus f at x. Exactly that expression there. But we don't have this expression in the numerator. Okay? Now I'm going to say something that's going to might sound a little crazy here, but just follow me here. It would be really nice to have this expression in the numerator, and it's not there. So you know what I'm going to do? I'm just going to put this expression in that numerator. Okay? I'm just going to do it. And then we can fight about whether what I did makes any sense. So I have my f at x plus h, g of x plus h. I'm going to stick in that expression that I said I needed, minus f at x plus h, g of x plus h. And then, of course, I still have the minus f at x g of x. But I just put something new into the expression, which means I changed it. And I'm not allowed to just stick new things into expressions, okay? Unless I do something else. What could I do that would allow me to subtract f at x plus h times g of x plus h? What else could I put into this expression that would make this okay? So imagine this was a 4. I just did a minus 4 out of nowhere. I just changed the expression. What could I do to undo that change?
All you have to do is just do the opposite of what you're doing.
Exactly. I'm allowed to subtract to this expression if I also add it. Now, I know it's probably been a really long time, but if you remember back in grade 10 math when you were completing the square, you used this trick in the past. And don't forget the f at x, g of x, okay? So do you see why this is legal? Because I subtracted this expression, but I also added the expression. So in the end, they cancel each other out. So have I actually changed the expression? No. Now, when you look at it, you go, oof, wow, this looks way more complicated. But look at what we can do in that first one here. Now we can do what we said we wanted to do. Factor out the g of x plus h, g at x plus h. So now I'm left with f at x plus h minus, sorry, f at x. Sorry, folks, that was a mistake on my part. This should have just been f at x. Remember, that's what we had earlier. I just realized this is what we needed to subtract. My mistake. Sorry about that. Sorry, very silly. Let me fix that. Let me fix that. Very silly on my part. Didn't realize that till after I wrote it. So. Okay, so same thing. I subtracted and I added it. So now I'm left with f at x plus h. Here, I'm just left with the minus f at x. Okay, and that's really good because that's the expression that's in my derivative of f formula. Okay, problem is now I have this extra thing hanging around. But I want you to look at these two expressions. Can you see what I can do with those two expressions? Look at those two. What can I now do?
Factor out f of x.
We can factor out an f at x. But not only can we factor out an f at x, look what's left in the bracket. G at x plus h minus g of x. Exactly the expression that one finds in the derivative of g formula. Okay? So while this might have seemed like a bit of an odd thing to do, that we took a simpler expression and made it more complex, this trick now seems to be creating some very nice things. Okay, so now let's do some more algebra here. And I'm going to split these up into two fractions. Okay, g at x plus h. And here we have f at x plus h minus f at x all over h. And here plus f at x times g at x plus h minus g of x all over h. Okay. And can you see here that this is a product up here? I can actually rewrite this as g of x plus h, okay, then times, and write it this way. Can you see how these are the same? Because here this is like g of x plus h over 1. So if I multiply the two fractions, I get exactly what I had before. Okay. And I'm going to do the same thing here. Okay. And look what we've done. We've managed to rewrite this expression so that I've got g all on its own. I have the derivative of, this expression that looks like the derivative of f all on its own. I have f all on its own, the expression in the derivative of g all on its own. Okay, and I'm now taking the limit of all these things. Okay, let's see. What is, if I look at just this part, what is that approaching? What is the limit of f at x plus h minus f at x all over h? What is this equal to if I take this limit? It's just f prime at x. So this is approaching f prime at x. Same thing here. This, when I take the limit as h approaches 0, just approaches g prime at x. Okay? Here, f at x, is there any h here? Is this affected by h approaching 0? No, there's no h related to this expression. So it just stays the same. It acts like a constant in this limit. It's not changing as h approaches 0. Okay? Sorry, that was g prime of x. And here, well, wait a minute. H is approaching 0, so what's happening inside that bracket? The thing inside the bracket is just getting close to x. So this is just approaching g at x. Okay? And so what do we have when we take the limits of all these parts? Okay? Well, the first expression just approaches g of x. The second expression approaches f prime of x. Then plus, this just stays the same, approaches f at x. And this expression approaches the derivative of g of x. And what we just found was a product rule. We showed that the derivative of a product is not the product of the derivatives. It's not as nice as that, but we kind of knew that wasn't going to be true. But the derivative of this product is just the second function times the derivative of the first function plus the first function times the derivative of the second function. So while it's not the easiest of derivatives, it does involve just the individual functions themselves as well as the individual derivatives. Okay? And the way we can write this rule in a more sort of a quicker way, okay, is what we often say is the derivative of a product, okay, is equal to, I'm just going to flip these around, which is fine because, you know, it's just a product, so you can write it in any order, is, and listen to the way I'm saying it. I'm not trying to memorize a formula. This is a big trick that I can give you with these rules, is try not to memorize it according to the letters, is try to memorize it, excuse me, according to the position of the function. So what is this saying? I take the derivative of the first function and I multiply it by the second function. Then I add to that the first function and multiply it by the derivative of the second function. And this, folks, is the product rule. Okay, give me just a second here. Now, with this proof, I skipped a little step on the justification, but we're not going to worry about that. Okay, because we essentially justified what was happening. But what we see here is we see how we prove things in mathematics, that sometimes you have to think of something clever to do. And the thing that was clever that we did in the proof is we included this term that allowed us to eventually create something that looked like the derivative of f. And then by adding that same term, we were able to then create an expression that was part of the derivative of g. And then by splitting up, using algebra very cleverly, we were able to come up with the rule. Okay? So now this is where we're starting to come up to stuff that's very, very useful, because I'll do an example here. Let's say I want to find the derivative of here. Let's actually include some of the functions you did before. Let's say I want to find the derivative of x squared times e to the x. Okay. Well, it's a product of two functions. So let's now apply our rule. So the rule says, take the derivative of the first function. What's the derivative of x squared? It's 2x. Okay. So I'm applying the rule. Derivative of the first function. Okay. And then I multiply that by the second function. So this is just times e to the x. Okay. And then what does the second part of the rule say? It says plus the first function, which is x squared, times the derivative of the second function, e to the x. So here, plus the second function times the derivative, sorry, the first function times the derivative of the second function. And of course, the derivative of e to the x is just e to the x. And so here we have the derivative of the product of these two very basic important functions. And what's nice about the product rule is it just uses the individual derivatives plus the functions themselves. Okay. So any questions? So I wouldn't worry so much. The proof was just to kind of show you where it came from. Hopefully you were able to follow the steps. But in the end, what's going to be important for you in this course is that now you have this formula to find the derivative of any product. And this is an example here. Okay. Any questions we want to ask about the product rule itself or the example that I did? Okay. So again, what I suggest you do, what makes it easy to memorize it, is to, again, think about position. Derivative of the first times the second plus the first times the derivative of the second. So it doesn't matter whether these functions are called f or g or whatever they are, you're just thinking about their position in the product. Okay. So let me give you a couple of examples here for you to work on to apply the product rule. Let's see, come up with a second function here, I guess. All right, so let's take a look at these examples. These are what I want you to work on. So here, just apply the product rule as is. Here again, you're just going to be applying the product rule. Here I'm adding a little bit more. I'm asking you, determine when this function, which you see is the product of two functions, has a horizontal tangent. So think about how first you would have to take the derivative, what's special about having a horizontal tangent, and then solve for that. And lastly, just to kind of check that this rule we came up with, just to check that I didn't kind of pull any kind of magic tricks on you here, that what I did is reasonable. I want you to find this derivative using two ways. I want you to find the derivative by first multiplying it out and then using your power rule and your sum rule to find the derivative. And then I want you to find the derivative using the product rule. Okay, and then check that both of those two answers give you the exact same result. Okay, so you might have to do a bit of simplifying to show that they give you the same result. Okay, any questions on what I'm asking you to do here? No? Okay. So let me give you, I'm going to say maybe 10 minutes to work on these. Okay. And if you want to ask me some questions, you can just put them in the chat. Okay. And I'll take a look at that. So like I said, let me give you about 10 minutes to work on these. So at about 8:27, we'll come back and have a look at them. So please ask me questions if you have any. All right, perfect.
Hello.
Hi there.
Oh, I have a I have a unrelated question to this.
Yeah.
What's the natural log times e?
So
Like,
let me make sure I understand what you're asking, because I think I know what you're saying, but let's make sure. So here, when you have just the natural logarithm,
mhm,
this thing on its own is meaningless. Okay.
mhm,
It's just the letter L plus the letter N. Okay, you're
Mhm.
taking the natural logarithm of something, so the natural logarithm of a number, because it's a function, right? Okay, e itself is a number, and then it could be the base of a function. So are you asking me what is the natural logarithm of the input e? Is this what you're asking me?
Yes.
Okay, good. So we want to make sure that we're clear that this is not a multiplication. Okay, so for
Okay.
example, if I write square root, does this have any meaning? Does it
No.
have any value? No, it's the square root of something. Okay, same thing with you know, sine. You know, this means nothing on its own. It's sine of, something, of an input. Okay, so
Right.
ln of e, this is where we have to remember what the natural logarithm represents. The natural logarithmic function is the same as the logarithm with base e of e. So remember what the logarithm represents. This expression represents the power of the base. Okay, so let's say it's the power of the base that's equal to e. Well, wait a minute. What power of e would be equal to e?
Wait. So we get EX because the log, the base 3 log E. So can you go back a step? There.
Yeah, let's go back. So when we write log base a of x, say we give it a name, ax, what does this represent, this expression? Another way of understanding this equation is it's saying that the base of a to the power of y is equal to the input of the logarithm. Okay, do you remember that this is the connection between logarithmic expression and rewriting it as an exponential expression?
Yes.
So when I write log base 4 of 16, what does this represent? If I call this number x, what is x? It's
It's
the power of 4
mm,
that's equal to 16.
okay.
And what would the answer be here?
2?
What
Is it?
power of, exactly. So
Mm,
log base 4 of 16 is equal to 2, because 4 to the exponent of 2 is equal to 16. So if I want to give this a name here, if I want to figure out log base C of E is, well, what this represents is what power of E is equal to the number E. So what would the exponent be here so that these two things were equal?
1?
Exactly, because this is e to the 1. So this is equal to 1. Log base E of E is just equal to 1. So natural logarithm E of E is equal to 1. Okay, so equal to 1. Okay.
Oh,
In fact, this is true for any logarithm. What's log base 5 of 5? Well, 5 to what power is equal to 5? Just 1. What's the log base 17 of 17? Well, 17 to what power is equal to 17? 1. So this is just a special example of all these, that when I take the logarithm of a number which is its own base, the answer is always equal to 1. Okay? Does that
mm,
answer your question?
yeah, it is.
Okay, excellent. Okay, so we got another minute or so to work on these. It'll give you up until 27, so I'll give you an extra minute to keep working on these here. Or if you need more time, let me know, by the way. I'm giving you 11 minutes, but if you need more time, just let me know. Okay, so I'll check in with you in 2 minutes. Okay, so do people need more time to work on these? Let me know if you'd like more time to work on it. Last call? No? Okay. So let's take a look at these examples together. Okay. So we'll start with this first one here. So I have f at x is equal to x times sine x. Okay. And I just want to find the derivative. Now, remember when I gave you that tip about finding the derivative is not memorizing, f prime g plus fg prime, because that means I have to give the name f to x and the name g to sine, and I already have this other thing that's called x. But by thinking of that formula in terms of the position, like I did before, remember how I thought of this formula. I said, it's the derivative of the first function times the second plus the first function times the derivative of the second. And so that's how I'm going to take this derivative here. Okay, so I'm going to take the derivative here by saying the derivative of the first function, the derivative of x, is equal to 1 times the second function, sine x, plus the first function, x, times the derivative of the second function, cos x. And so my final answer is just sine x plus x cos x. Okay? So similarly here, let's look at number 2. So number 2, f at x was equal to root x times cos x. Now, you're going to get to the point where you won't need to do that, or maybe you already feel comfortable not doing this, but you might want to first rewrite this as x to the 1/2 times cos x. Okay, so that you're rewriting it as a power. So now I can take the derivative. Okay, and what do I have? Well, the derivative of the first function is 1/2 x to the negative 1/2 times the second function, cos x. Okay, and plus the first function, x to the 1/2 times the derivative of the second function, negative sine x. Okay, and now we can leave it like this if they're telling you not to simplify it, or we can clean it up a little bit. So here, x to the negative 1/2 will go to the denominator, come x to the 1/2. Okay, and then here we have, or this will become minus x to the 1/2 sine x. Okay, and we can even make it a little simpler by turning these back into square roots. So 1 over 2 root x. In fact, we can even put the cos x in the numerator, multiply these out, and then minus root x sine x. Okay, and that's about as, it's about as simple as I think you can get it. All right, any questions on either of these first two? No? Okay, so number 3 asked us, where the function y equals x e to the x has a horizontal tangent. Okay, so what has to happen in order to have a horizontal tangent? Who's going to remind me what needs to happen in order for the function to have a horizontal tangent? Help me out here.
Basically, if we want to have basically you have to get the derivative first, and after that,
Yeah,
set the equation to 0, since y is
exactly.
0.
So in order for this to have a horizontal tangent, y prime has to be equal to 0. Okay, this is what we're having to solve. So as was said, obviously, if we want to solve this equation, we're going to have to take the derivative of x e to the x. So now I'm going to apply my product rule because it's a product here. So derivative of the first function, derivative of x is just 1 times the second function, e to the x, and then plus the first function times the derivative of the second function, e to the x, and all of that has to be equal to 0. Okay, and so now what can I do to solve this? Can you see something very nice that I can do to solve this equation? Because right now, as it is, I can't solve for x directly, so that's not going to help. What can I do with this expression on the left that will allow me to solve for when it's equal to 0? So let's look for some ideas here. There you go, is factor out the common factor. So I'm going to factor out the e to the x. What am I left with? 1 plus x equal to 0. And now I have the product of two expressions equal to 0. So that means either the first one is equal to 0 or the second one is equal to 0. Now this one's very easy. X equals -1. When is e to the x equals 0? There's a couple of ways we can answer this question. When is e to the x equals 0? What value of x makes e to the x equals 0? Can anybody tell me that? Ah, there you go. See, again, didn't fall for my trick. So here, remember with e to the x, you can look at it as a graphically, and you realize, oh, hey, e to the x is always positive. So there is no answer, okay? Or I could try to solve it by using logarithms. And if I try to take the log base e natural logarithm of both sides, here I just get x, but what is ln of 0? And you realize the natural logarithm is not defined at 0. We say it does not exist. It can never be true. Okay, so whether you remember what the graph of e to the x looks like and realize that it's always positive, it's never equal to 0, or if you try to solve by using logarithms, you end up having to take the natural logarithm of 0, which doesn't exist. Okay, so this is the only x value where you have a horizontal tangent. Okay, and if you want to find the point, well, you can just stick it into your equation. So -1 times e to the -1. And what does that give me? Well, this will go into the denominator, so -1 over e. So the point would be at -1, -1 over e. Okay, this is the only place where this function has a horizontal tangent. Okay, if you put it in Desmos, if you plot it or whatever you use, I see WinPlot, but I don't know, hopefully do folks use Desmos?
Yes.
Yeah, okay, definitely use Desmos, much, much nicer. Okay, and there you go. So now the last question I asked you to do was to kind of confirm that the product rule makes sense. So I asked you to first find the derivative using distribution, and then to find the derivative using the product rule. And let's make sure that we get the exact same answer, because if we don't get the same answer, we got a problem. Okay, so here, if I take this question here, and let me start with, option A. So I'll first distribute the x. So what do we get? We get x cubed plus x. And so that means that the derivative is just going to be 3x squared plus 1. Okay, so this is first distributing and then using our power rule. Okay, now let's try option B. Let's do the product rule. Okay, so the derivative of the first, 1, times the second function, x squared plus 1. Okay, plus the first function, x, times the derivative of the second function. Well, what's the derivative of x squared plus 1? Well, it's the derivative of x squared plus the derivative of 1. So derivative of x squared is just 2x. And then the derivative of 1, well, that's just 0. Okay, and you might look at this and say, well, these don't look the same. Remember, I said you might have to do a little bit of this. You have to do a little bit of simplifying. So x squared plus 1 plus this is going to be 2x squared. And lo and behold, what do we get? 3x squared plus 1. The correct answer. Okay, so this kind of shows that, you know, this product rule we came up with seems to make sense because you get the same answer as you would if you solved it a different way. If you didn't, it means there was going to be a problem with our formula. Okay. Now, in this case, there's an argument to be made that this was easier to first distribute. So in a case like this, I probably wouldn't use the product rule. It would make more sense to first distribute. But if I was taking the derivative of, oh, I don't know, maybe, you know, the derivative of x squared plus 3x minus 7 times x cubed plus 4x squared minus 3x plus 5, well, I'm not very motivated to distribute this first and then take the derivative. I think I would much rather use the product rule to solve this derivative. Okay, so it all depends on the situation. Here, easier to distribute than take the derivative, little bit less time. Here, much faster to use the product rule than to try to expand it first. All right. Okay. Any questions on the product rule here? All right, so what I would say at this point, so we've got 20 minutes left, so I'm going to say there's one of two things we can do. I could give you a few other examples, or if you want, I noticed that in the content, I guess each of these sections has a little assignment, so I don't know if you want to get started on that. Okay. Or actually, there's option 3. Option 3 is if you want, I can try to start going through the quotient rule if you like. So those are our 3 options. We can either, I can just come up with a few more examples to give you. You can start working on the Brightspace stuff, which I'm assuming you have to do at some point, or we can go to the quotient rule. So I don't know, who's the guy who did or the woman who did the poll here? Who did the poll last time? Who is that? Here. Oh, Amit, that was you. Here, do you wanna? Okay. So I guess remember option 3 is doing the quotient rule. Okay, anybody else? Quick. Okay, so far we got a lot of quotient rules, so if not, give you 5, 4, 3, 2, 1. All right, looks like we're doing quotient rule. Okay. Thanks for doing that poll there for me. All right, so now what I didn't tell you about doing the quotient rule is we are going to prove it, because, you know, that's what you get when you got a math person who comes in, is they like proving things. Okay, but I don't know, hopefully you find it a little bit fun because you're getting a little bit of a sense of how mathematics works when we have to actually do things a little more abstractly. Okay, so the good news is we are not going to be using the limit definition. Okay, and it comes down to this. It comes down to the fact that multiplication and division are, you know, they're related to each other. Okay, so usually if you can come up with a rule for multiplication, it can then help you to come up with a rule for division. Okay, so what we want to do here is we want to find the derivative of a quotient. Okay, I want to find the derivative of f at x over g of x. I know it's not the quotient of the individual derivatives, okay? But because I do not want to put this, if I can avoid putting this in the limit definition, that's going to make me very happy. So what I'm going to do is I'm going to give a name to this quotient function. I'm going to call it h of x, okay? I'll say let h of x equal f at x over g of x, okay? And this is where, again, somebody at some point had a very clever idea. They said, you know what? If I can take this and turn it into an expression that has, or an equation that has a multiplication in it, okay? The product of two functions. Now, some of you might be thinking, hey, wait a minute. I can do f at x times 1 over g of x. That's a product, and it's equal to f at x over g of x. The problem is I don't really know how to find the derivative of 1 over g of x. I want the product of two functions. I don't want the product of one function and the reciprocal of another function. So while this is, a good start, we're just end up with something else we don't know how to do. So what we're going to do instead is we're going to multiply the g of x to the other side of the equation. Okay, and we're going to rewrite this equation as f at x equals g of x times h of x. Okay, perfectly legal. Oh, my thing's just, oh, there we go. It's a perfectly legal thing to do. I just, multiply both sides by g of x. There you go. But now look what we have on the right-hand side. We have the product of two functions. So now I'm going to take the derivative of both sides of this equation. Okay. Now, you're going to notice that from this point forward, I'm going to use the prime notation. So on the left-hand side, hey, it's just the derivative of f. There you go. But now on the right-hand side, I have to use the product rule because I have the derivative of a product. So let's follow the rule. It says derivative of the first, so g prime of x, times the second function, h prime of x, plus the first function times the derivative of the second function, okay? But this is where I want you to see that isn't h prime of x exactly what we're trying to find? H prime of x is just equal to the derivative of f at x over g of x. This is exactly the thing we're looking for. So since the thing we're looking for is in my equation, I'm just going to solve for it. Okay, so let's see, let's bring this to the other side. So we have f prime of x, and so here now we're going to subtract g prime of x, h of x. Okay. And now, well, there you go. I can divide both sides by h prime of x, sorry, by g of x, sorry, f at x prime of x minus g prime of x, h of x all over g of x, okay? And look what we have. We have a formula for the derivative of f over g, but wait a minute, it's got an h in it. I don't want to have an h in it. Well, but remember, what is h equal to? It's just equal to f at x over g of x. So let's replace that in our expression. And look at that. We have a formula for the derivative of the quotient that only uses the individual derivatives and the functions themselves. Okay? So all you have to do now is to memorize this formula. F prime of x minus g prime of x times f over g all over g of x. There you go. It rolls off the tongue. Would you agree? Isn't that really easy to memorize? What do you think? Is that easy to memorize? Oh, I was hoping you were going to say it was easy to memorize. Oh, well, okay. Of course, you know I'm joking. Yeah, this is terrible. Of course, you don't want to memorize this thing. This not, at least the product rule, it kind of rolled off your tongue, derivative of the first times the second plus the first times the derivative of the second. This is completely unintuitive. So, in order to hopefully make this a little better, let's actually do some algebra here, okay? You notice how you have a fraction up there. So let's see if we can simplify this a bit. Let's subtract this using a common denominator, okay? So here I'm going to have, so I have this divided by g of x. I'll leave that there. And then here, let's subtract these using a common denominator. So the common denominator would be g of x, okay? And what would we have? Oh, this part doesn't have a g of x in the denominator. So I'm going to have to multiply this by g of x. The second expression already has a g of x in the denominator, so I don't have to do anything to it. Okay? But now wait a minute. Dividing this whole fraction now is being divided by g of x, and hopefully you know that dividing by g of x is the same as multiplying by 1 over g of x. And finally, we're going to get something that is a little more intuitive to work with. So f prime of x, g of x, minus, I'm just going to flip these around. And you'll see in a second why I flip these around. F at x times g prime of x. And then all over, well, g of x times g of x is g of x squared. And that's equal to the derivative of f at x over g of x. Okay, because remember, that's what h was representing. G of x, f at x over g of x. And this, when you look at it more closely, do you recognize the numerator? Does the numerator not look familiar to you?
It's from the product rule or
With
similar
what?
to it.
Yeah, with only one difference. Instead of being a sum, it's a difference. Okay, so now let's rewrite this in a simpler way like we did before. So we have our product rule. The derivative of product is the derivative of the first times the second plus the first times the derivative of the second. And now,
Sorry, the
oh
g
yeah,
of x in the denominator, is that
oh
to the
squared.
power of
Good
2?
call. Yeah, good call. Yeah, remember we multiplied g of x times g of x. I forgot to write the square. Thanks for noticing that. Okay. And now let's write the formula for the derivative of a quotient. Well, it's the derivative of the first times the second minus the first times the derivative of the second all over g squared, the denominator squared. Okay, so a little bit more complicated than the product rule. As expected, division's always a little more complex than than multiplication. But what's nice about these two formulas is the order of the functions is exactly the same, except for a multiplication, the product rule, it's an addition, and then for the quotient rule, it's a subtraction. So f prime g plus fg prime, f prime g minus fg prime. And of course, we have to divide by, the square of the denominator. Okay. So I'll give you an example, and then we'll have just enough time for you to do a couple of exercises. So as an example here, okay, if I want to find the derivative, say, of x squared divided by e to the x, okay, so we did the product of these two functions. Now let's find the derivative of the quotient of these two functions, and let's follow the rule. So derivative of the numerator, 2x, times the denominator function. Okay, minus the numerator function, x squared, times the derivative of the denominator function, still e to the x, and then all over e to the x squared. Okay. Now, this is not the simplest of functions. You notice that the derivative is much more complex than the original function. Okay. Can anybody see how we can maybe simplify this a little? Can anybody see any nice way we could simplify this? What do you notice about the two terms in the numerator? Oh, sorry, I just saw somebody put in the chat. Yeah, let's factor out the e to the x. If I factor out an e to the x in the numerator, here I'm left with 2x minus x squared. But now I can reduce the e to the x in the numerator with one of the e to the x's in the denominator, and at least I get something a fair bit simpler. There you go. And there's your derivative. So actually looking still more complex than the original function, but not quite as bad as it looked originally. Okay. So what you now have is you have the ability to take the derivatives of sums, of differences, of products, of quotients, of powers of x, plus all those other basic derivatives that you had last time or from the previous unit. Okay. So let's give you a couple of examples, but now that we have the quotient rule, we can add another group of functions for which you can find the derivative. You can now find the derivative of any rational function. Okay. Whereas in the past, you could only do it for very special rational functions, but now you can find the derivative of x squared plus 1 over x squared minus x. This is not something you had the tools to do, but now that we have the quotient rule, you can find this derivative. Okay, so let me give you this one here and maybe one more, and then we'll call it a night. Okay, so let's say we'll do ln x over x squared. There you go, just to give you something. Wait, did you folks do the derivative of ln x? Somebody confirm if you did that? You might not have done that in this course. It's not technically in the curriculum. So you know what? I'm just looking at the time. It's 8:55. Let's just do this question here. I'll give you another one in case you finish before the others, but do just this one here. That's the only one I'll take up in about 2 minutes. Yeah, you can do this one here as a bonus one if you finish the other one, okay? Okay, so let's take a look at this one here. So here, there's no simplification I can do to solve this another way. I have to use the quotient rule. So let's follow the rules. So remember, the derivative of a quotient is f prime g minus f g prime over g squared. Okay, so let's take the derivative of the numerator function. Derivative of x squared is 2x. Okay, derivative of 1 is 0. Okay, so that's done. Times the denominator function, x squared minus x, minus the numerator function, x squared plus 1, times the derivative of the denominator function. Derivative of x squared is 2x. The derivative of x is 1. All over x squared minus x all squared. Okay? So this now gives me the derivative. But of course, if I need to actually work with this derivative, I should simplify it. So let's simplify the numerator. So let's distribute here 2x cubed minus 2x squared minus, make sure you put brackets here. Let's distribute this, x squared times 2x cubed minus x squared plus 2x minus 1. And now let's do some more simplifying. The 2x cubed minus that 2x cubed, so that's gone. Here we have negative 2x squared plus x squared, so negative x squared. Here we have minus 2x, and here we have plus 1. And there you go, over x squared minus x squared, and there you have it. Okay, and then you could see you might be able to factor the numerator. Looks like that is a possible, well, no, actually, I don't think it's going to end up being factorable, but that's as far as you can go. But now that means you can find the slope of the tangent for any rational function. Okay, and that brings us right to 9 o'clock. Okay, right on time. We'll call that a night, and good luck with the rest of your course. Okay, and I will post these videos as soon as I figure out how to upload them. Okay, have a good night,
Good night,
everybody.
sir.
Thank you.
Bye, sir.
Have a good night. Thank you.
You too. Take care.
Thank you so much. Have a good
Okay.
night.
You too. Bye-bye.